I will talk about the multiscale modeling and the simulation for non-Brownian dynamics. Mostly, we consider the talk will consist of the five parts. First, we give a brief introduction to anomalous dynamics. Then we discuss the mathematical modeling. The so-called mathematical modeling is based on build the stochastic process to describe some natural phenomena. Then we, based on the stochastic process, will derive the PDE. Okay. Then we will derive we consider the statistical observables or those stochastic process. The way of discussing the properties of statistical observables is to try to calculate the probability density function of statistical observables. How to calculate is we will try to derive the equation that governs the PDF of the statistical observable. Then when we get the PDEs, for example, the Fock-Planck and Feynman-K equation, then we try to do some analysis and numerical algorithm. Then we further discuss its applications in chemistry and biology. First, there are a lot. This background. This is about the background motivation of the non-Brownian motion, non-Brownian diffusion. This is example of the first slit diffusion of protein on DNA, and another one is forked mediate diffusion. So for this model, this is a jump process, and for this model, for the PDE, generally it is a one-dimensional PDE coupled with a three-dimensional PDE. If we consider the governing equation of the statistics of observable, some particular statistics of observable, for example, the position, functional distribution, the functionals, and or the mean first exist time or escape probability. All these kind of statistical observables, generally the PD is one-dimensional PD coupled with three-dimensional ones. Yeah, this is subdiffusion case. This is still in the cells, the individual cells is the movement of the particle. Then you can see the average, the second moment is not a linear function of t. The second moment is not a linear function of t. Is t to power alpha. Alpha is not equal 1. So when alpha less than 1 is a subdiffusion. For this case, is the super diffusion. For example, the particles the move in this on this line. Then at here is target. Then it in some sense it makes a huge jump. More case is a fast sliding diffusion and the 3D hopping diffusion. And also the polymer dynamics is the new in recent years some new kinds of non-Brownian motion. The new case, in some sense, it's violate the central limit theorem and the generalized central limit theorem, because the second moment of the stochastic process is a linear function of t, but the probability density function is not Gaussian. So this not mathematically is generally we cannot predict this kind of phenomena, but in the experiment we can observe this kind of call it Brownian non-Gaussian case, Brownian non-Gaussian Brownian motion. So based on this kind of phenomena, then we try to build the models to describe this kind of phenomena. One way is is considered the case of polynomial, because when the polynomial has a big number of monomers, when so we consider the motion, central mass of the motion of the polymer. We consider the position of central mass. Then generally, if the number does not change, then obviously it can be a Brownian motion or non-Brownian motion. For example, it can study subdiffusion or super diffusion. But when the number is changing, number randomly changes, that you huge number of monomers, the number, it can increase or decrease the fluctuation, the number of monomers with fluctuation. Generally, we can the process, so it implies the diffusion coefficient is random. So in this case, after doing some analysis, you can find it's no longer cannot be just described as a Brownian motion or superdiffusion or superdiffusion or subdiffusion, but it can behave like Brownian non-Gaussian case. So all of these cases, all the previous discussion is about the biology or chemistry background. In fact, even for it's called the anomalous is normal. Even in our daily life, we still can find the non-Brownian case, non-Brownian motion. So this is a typical example. This is in middle school we understand the Newton's second law, but when we study the calculus, the Newton's second law can be described by Lagrange equation. Even for this our daily life. In our daily life, we can this Newton law. So the Newton's second law. So we can we can consider as a movement of small particle in the table, and the particles will move because of wind or something. It can move. So this is the force. The right hand is force. We can consider particles impacted by the environment. The environment can be the wind, everyone can be breeze, or in the wind from the window or from the door. That all makes the particles to move. Then we can build the equation. This is all the force comes from the environment. Here is friction coefficient. So this one is a potential, and it implies the table is not so smooth. So it's a very simple model. But even for this simple model, it can be it also follows Newton's second law. Is in our daily life, we can consider the particle in dust in our living environment. So when do some analysis, you can do simple analysis for the xt. Obviously, it is a stochastic process. You can do the simulation by Monte Carlo simulation, and you can also even in the lab we can find very rich dynamics, non-Brownian dynamics. So we call it anomalous is normal. It implies Brownian motion is not anomalous case is also very popular. So generally we can describe we can do the classification of anomalous case. For first one is localization. This localization case, if the particles move within the case of its potential, well, this is normal. We can it is our expectation. It behaves like this. But even in fact, even for the free particle, for example, fractional Brown motion, it is possible to have the particles for even the free particle. The area is can be in the average weight can be in the bounded domain for the second moment. Also, for if we based on the square MSD to do the classification, when alpha is bigger than 0, less than 1 is subdiffusion, and for t, x square of t is a linear function, t is a Brownian motion. But there are some new observations, as I just said. Sometimes if even is linear function of t, for Brownian motion, the xt is the PDF or xt must be Gaussian distribution. In some cases, in some new observations, is the PDF or xt can be, even though this one is a linear function t, but the PDF can be exponential diffusion or some other diffusion. So there are still some new discoveries. For the others, for the alpha is bigger than 1, we can call it super diffusion. Also, it's possible for there are also some observations holistic diffusion. This is a polymer diffusion. We have polymer diffusion as I just described. It can be this one. Second moment, second moment of xt is a linear function of t, but the PDF is not Gaussian distribution. There are also another notion is a strong anomalous diffusion. For Brownian motion, generally the Q's moment is generally is T o half Q over half. The moment is T2 Q over half for Brownian motion. Generally for the moment, the Q's moment or stochastic process is a linear function of Q. Generally we call it the diffusion, general diffusion. But if not a linear function, we call it strong anomalous diffusion. So we do the so-called mathematical modeling. Because the mathematical modeling is to build the stochastic process to describe all these kind of observations, all these kind of experiment observations. We try to build some stochastic process to describe it. We expect we can discuss the so-called mechanism of the motion of the particles. Then we can hope we can calculate some statistical observables we expect to observe to make the stochastic process behaves like the particles of experimental observation. So the framework is the first one is based on the so-called the CTRW model. It is very often used by the statistical physics community. And another one is the Lagrange equation. As just one we give example. This is a simple example of Lagrange equation to define a stochastic process. The typical one is the so-called Levy walk, and also CTRW with multiple interval process, and the Levy walk is multiple internal states. Another one is in this framework. Sometimes for the process we can use for the two ways to describe a particular stochastic process. But sometimes, in some cases, one of which has some advantages to describe the particular case. For example, in Lagrange equation, if we consider a stochastic process with the movement of particle with external potential, generally we can use it's convenient to describe the process under the framework of Lagrange equation if it has an external potential. You just add an extra term to the surface, and in this framework is a little bit complicated to consider the case with exponential potential, because you must transfer the potential to the jump length or waiting time. Another one is diffusivity. This way. Diffusivity means the stochastic we can get the stochastic process has a stochastic coefficient. And also we use some ways to get a new stochastic process by doing some time change to the existing process. For example, we can do the time change to Brownian motion to get the Levy process. I can also do the time change to the Brownian motion to get the process which can characterize the subdiffusion. But the time change process is still a process. Time is one from R to R1. And another one is also can do some other process is alternating process or resetting process. After building some new kind of based on the observations, we can build various kinds of stochastical process. Then we try to analyze or derive some. We can do the analysis of based on the observations, based on the experimental observation. We need to do the statistical observables. We need to study some particular statistical. The statistical observables, the typical one can be position, for example, velocity, functional, mean first existence time, escape probability, are also a lot of typical. This we just list several ones. Then how to do this? We can the way to study this statistical observables is to get because this one is also all of this is random variables. Random variables. So the way so we do it is to get its distribution, quantitatively to derive to get its distribution. The way of get quantitatively to get its distribution is derive describe it is the probability density function. The way of deriving is probability function is to quantitatively describe it is to derive the PDE governing the PDF. So if you consider the position and corresponding to the Fock-Planck equation, if for the joint distribution of velocity and position, you can derive the Clement equation. If we can describe the position and the functional joint distribution of the vertical statistical observable, we can derive the forward Feynman-K equation. If we just concern about the functional, not the joint distribution, we can derive the backward Feynman-K equation. Also, if you are concerned about the escape probability, you can derive the equation on the is non-time independent ones. Also, if we can also calculate the first mean passage time. This one is not a PDF, but we can also derive the governing equation for this one. The mean first mean, the equation on mean first is also in time independent PDE. So briefly introduce the CTRW is extremely simple for the continuous time random walk model. It is a compound renew process. It's compound renew process. For the first one is if the waiting time tau I is lambda e to power lambda t is compound Poisson process. For example, if tau I follows obeys exponential, but Ci or obeys power law distribution or Gaussian distribution or some other distribution, you can for different kinds of distribution, you can define different kinds of stochastic process. You can consider this case if tau I is the renew process is not a Poisson. For example, renew process if tau I follows the power law ones, we can define a fractional compound Poisson process. For this one, if for compound Poisson process, if Ci obeys this distribution, power law distribution, then we can get the Fock-Planck equation. This is a fractional Laplacian operator is the integral form to define the operator. Also, if the functional is just talked about the functional, define the function. This integration of u is a specified prescribed function, and xt is a stochastical process. If we consider about this function, the distribution of a, then we can derive the forward Feynman-K. This is the joint distribution of x and a. In fact, we do not directly get the distribution of x to a, and we get the p is a Fourier pair of a. P is a Fourier pair. We do the Fourier transform from a to p. So the equation we derived is ux, the joint distribution of x and p. So there's a Fock-Planck equation for that process with Poisson renew compound Poisson renew process with jump length of KCI. KCI jump length follows power law x to minus beta minus 1. Yeah. So we can quantitatively study to solve this equation. We can get the joint distribution for UXPT. You can also derive the backward Feynman calculus. This one x0 is the starting point. It's just the parameter. It's just the parameter. So we just get the previous forward one is joint distribution of position and functional. But here is just a distribution of functional. It's no x. Here x is just a parameter. It's a starting point. So it's not a joint distribution. So if you are just concerned about the distribution, or not the joint, you don't concern the distribution x, you can use this equation. We call it the backward equation. Also, we can derive the mean first passage time. If you concern about this quantity, this statistical observable, you can solve this equation. Ux is the mean first passage time of the process. So this is a Levy process, and also you can calculate the escape probability by solving this equation. This equation, because the process is jumping process, so this also is a physical quantity. If Levy for Brownian motion, we don't have this quantity. This concept is escape probability, because for Brownian motion, the particles cannot jump from D to E. It cannot from D directly from D to jump to E. So this physical concept also implies how to specify the boundary condition of this kind of PDE to make the PDE to be well posed. This also the physical motivation, how to make the PDEs to be well posed, how to specify the boundary condition. This also in some sense also can be the physical meaning of the boundary of the PDEs. Yeah, there is also a lot of stochastic process. Is the Levy walk. Levy walk is another little bit different from that's Levy flight. This waiting time is a power law, but the jump length depends on tau I. Because the particles moves with a fixed velocity, but the direction is still random. And in this way, for this process for Levy walk, it has two modes. First one is the central part, another one is the ballistic part. Because of this, we introduce some new concept appears, for example, as so-called strong anomalous diffusion. Because for this one, we cannot use just use the central limit theorem to describe it. We can use for the central part, it can be described by central limit theorem, but for the ballistic part, you must use infinite covariant density to describe it. Also, you can use other ways CTR. For example, the CTRW model is scaling limit of the time change the Levy process. We can do if we can do the time change, do some time change, we can get this kind of process. This kind of after do the time change, we can derive the corresponding Fock-Brown equation, and also forward the Feynman equation, and also can derive the backward Feynman but is for the trivial case, the mean first spacetime is positive infinity, so you don't need to solve equation. It's trivial, but we can still solve the escape probability. And other ones is with multiple internal states. It implies when the time change, we use a Markov chain to make choice when the particles we do the renew or the renew process. When the time is need to renew, we have several choice to follow different distributions. For the real choice, we use a Markov chain to describe it. So it has a probability to enter a specific probability distribution. then the random variable can be generated by you randomly choose the distribution, then you get a random variable for the jump lines for basically the multiple internal states. And yeah, now it's a system for the equations is a system, not a scalar equation. So you can derive the Fock-Planck and also Feynman-Kai, forward Feynman-Kai and backward Feynman-Kai. And also you can discuss this kind of function. We can consider how long it stayed, for example, how long it stayed in the particular state. Then the way is still a random variable. The way to quantitatively to analyze it is to get its distribution. How to get its distribution? We derive the PDEs that governs the distribution of the random variable or the statistical observables. In fact, this one have some very important applications. It can solve some challenging problems. First, physically, if the problem is if the process is with multiple internal states, we need to use this kind of model to describe it. Sometimes even the physical problem is not a process, physically is not a multiple internal process. But this framework still help us to solve some challenging problem. For example, this is a simple example. We can mathematically to get illustration to how to use it. For example, if a stochastic form comes from this way, it cannot be generally do not hope it can be immediately to goes back. It can just go to these three cases. For stochastic process, generally, if you use internal states, multiple internal states, it's harder to describe it. It's not just a simple inhomogeneous case. It's not generally inhomogeneous. So you cannot just simple specify a probability measure to describe the stochastic process. It's a hard problem. But if we consider it as multiple internal states, then this problem can easily to build a stochastic process to describe it. This is transition matrix. We can use Markov chain. For example, this one is this probability 1 over 3, 1 over 3, 1 over 3. This is 0. Yes. We will use 4 internal states to represent this state. So you use this transition matrix. We introduce the transition matrix, so you can easily in this framework, you can easily build the stochastic process to describe this kind of case. Another one, of course, is long-run modeling. The first part is mainly focused on the CTRW framework. Here we can also consider build a model, and in the long-run model in this framework, we use, for example, FXT, DLT, for example, with the potential, external potential. F is exponent, L is the layer process. We can try to derive the PDF of the process. XT. We can also for this we can also based on the time change to define the new process. First, we define the time change of alpha stable layer process starting from maps from R plus R from R to R. One-dimensional case square. So this way you can build some new kinds of processes. So all these are stochastic. So another one is the diffusive model. So as it describes the Brownian non-Gaussian case. Brownian XT follows the dynamics of XT is Brownian non-Gaussian because dXT is NT is birth death process NT is also a stochastic process, so it's a random coefficient. It's called XT. It has a random coefficient. We define the so-called diffusive model. Here is the define or definition of NT. it has the probability to transit from I, the number I, to the number of G with the probability. So the first part is we build the so-called models, the microscopic models. The so-called micro models is very kinds of stochastic process. Then we consider consider about how is some kinds of interested statistical observables. Then we derive a lot of PDEs governing the distribution, governing probability density function of the statistical observables. We derive a lot of equations. So further, we need to numerically to solve this equation or analyze the equation. Also, we can also directly analyze the stochastic process in the physical community. In statistical physical community, they can with some very good physical intuition to calculate some statistical observable quantity to do. But mathematicians feel that sometimes they're not so strict. But also we can by the probability analysis to do the probability analysis to the stochastic process. We can do the two kinds of way to study. Also, we can solve to study the statistical observables by numerically solve the PDEs or mathematically to discuss the well-posedness of the PDE. So there are a lot of mathematical problems now after get the new kinds of new stochastic process and new PDEs. And first way is we do some mathematical analysis and some numerical works. This one is for the Fock-Planck equation for the polymer diffusion. That means with a random coefficient. Is a discrete operator. Is infinite dimensional. This diffusion we can also call it derive the forward, backward, and Fock-Planck and forward Feynman-Kai and backward Feynman-Kai, and also alternating process. There are also three modes. Can also resetting process for this kind of process, new kinds of process. So can also derive the forward and the backward equation. And so now we turn to analysis. Firstly, we can do numerical for the probability analysis, stochastic analysis. We can find use the Feynman-Kai formula to analyze the. This is well-known result for the stochastic process. It has the Feynman-Kai formula. Based on Feynman-Kai formula to do the analysis, stochastic analysis for the PDE. For our case, for non-Brownian case, we can also do the similar things. Also, can derive the stochastic representation, then do the regularity analysis based on the stochastic representation. For example, for the Fock-Planck equation, we choose one or represented one. For the Fock-Planck equation, it can be expressed as in this form. First, we can derive is the stochastic representation. We can written is as in this form. This one we mathematically prove is a unique and is a unique mild or weak solution of this PDE. After this, then we can do some design the numerical schemes. For example, include the classical scheme, finite difference, finite element. Also, we can calculate by the deep learning method. For example, based on the BSD. For this one, we can discuss the finite difference scheme for the PDEs. It describes the operators by finite difference. This way. They'll try to describe the non-local operator and get the corresponding error estimate. Then we also can discuss the finite element scheme. We can also design the finite element. For example, sometimes this example very similar to if lambda equals 0, it reduced to the fractional Laplacian, and if the framework there are already some existing result for fractional Laplacian, how to the variational framework has been built, and how the analysis of the finite element analysis has been detailedly discussed. But for the operator, we have a lambda. Lambda is bigger than 0, big or is bigger than 0. If lambda equals 0, it reduced to the fractional Laplacian. But generally, we think we can simply use the existing ways to treat it. Here, we just want to see it's not even for the little operator with a simple change, with a little bit change. Some analysis cannot be directly applied to the case. So there are a lot of mathematical challenges for all the newly built the equations. This is give a simple example. For example, this case for lambda non-equal 0. First, is for lambda non-equal 0 is similar. We can build the variational form. For example, for lambda not equal 0, we use the symmetry of the non-local operator as a variational form. For this one, it's a non-linear form. We can non-linear form. So we can follow the ideas of a lambda equal 0 case to do the analysis. Then we can easily, by the Lax-Meyer equivalence theorem, you can prove it. We can get uniqueness, coexistivity, and continuity. But then you find that's not for the lambda equal 0. We can easily get this case, get this result. Then for lambda non-equal 0, we can expect it holds. We try to prove the coexistivity, right? Try to prove. But unfortunately, we cannot get the C is strictly than 0 by using L-Hospital ruler. You can find this, right? That means we cannot find a C, make it hold. So we just with lambda non-equal 0 cannot just the result of lambda is the case of lambda is equal 0 cannot be simply to apply to this case. So the way of overcome this challenge, we consider the domain with introduce new boundaries. Then we define the norm in the new boundary, new domain. The domain is expanded instead of the original domain. By this, we get the coercivity. So it cannot be just simply to generalize the existing result. So by this one, we just to emphasize all the new models have a lot of introduce bringing a lot of mathematical problems. They cannot, most of existing results cannot be easily or directly to generalize to these kind of models. We must bring you some new ideas to do the numerical analysis or well-posed analysis. Yeah, there are also, for example, for the operators with the substantial derivative, for example, call it the Fock-Planck equation. It's not so easy to generalize to just generalize the existing ways to treat the operator or describe the operator. We must consider some new ways. This is we do the discretization in frequency domain, then do the operator estimate. Also, we do some research works for the equation with noise, the PD with noise. The source term, when the source term is influenced by the has some is random, then we need to consider this kind of we need to solve the PDEs, the random PDE. Another way is also just mentioned is for the classical method. For some cases, it's infinite dimensional. For example, just mentioned the PDE is the diffusivity. The stochastic process is the Brownian motion with the random diffusion coefficient. In this case, the operator is with infinite dimensional discrete operator and also diffusion operator. Because this is infinite dimensional, so if you use classical method to solve it, you have to consider how to make a truncation. Right? But the natural idea is to use deep learning to solve it. Use a method of deep learning. So the way we try to derive the BSD to solve this way, we use deep learning method. We try to derive the BSD of the corresponding BSD of the PDE. So the several kinds of Fock-Planck, forward Fock-Planck, backward Feynman-Taylor, Fock-Feynman-Taylor, it can be abstracted to write in this form. So now we face we will treat how to numerically solve this one. How to numerically solve this one. In previously, we try to model. We so-called the model is stochastic process, and based on the stochastic process, we derive the PDEs. The PDEs is the deterministic equation. It's the governing equation of the PDF or statistical observable. From now, we can forget the stochastic process. This process is a physical process, which here we just consider how to solve this one. When we try to solve this one, we still need to introduce. We again introduce introduce the stochastic process. But here the stochastic is not the original physical process. This process serves for the algorithm. We introduce process to solve the. It's not the original physical process. It's this process serves for the algorithm. We try to use the process to generate the training set. The definition of the operator, discrete operator, is defined in this way. Then this is a diffusion operator, continuous operator. For the birth-death process, is the NT is the birth-death process. Is defined. But here this process is also physically is this definition. We use this operators. For the algorithm, for the numerical algorithm, we still again to consider the process. But this process, because motivated by it should have some connection because the PD is derived from that physical process. When we design an algorithm, we still consider some similar process. But another one is XT. XT is not the original process. Here is just we define a continuous random measure, and based on this random measure, we can define the XT. This process, this stochastic process, its function is it serves for the algorithm. Then this is the key. This is the key. We derive the BSD of the equation we are trying to solve. So this U and this U is the same U. This U is a solution of PDE. If we replace small n by capital and small x by capital X, we try to find the equation, the governing equation for this one. This U and this U is the same U. This U solves the PDE. We try to find what equation this one solves. This is what we do. We try to get the equation this one solves. NT is we decide the process. This is the birth-death process. XT is also we define the process. So we can mathematically prove this one solves the equation. This equation is called BSD. So we can generate a lot of samples, These samples is a training set. That's if we use these samples to train, then we can get U. If we can get U, then the solution PDE is got. This is the basic idea, how to use BSD to solve the PDE. Yeah, after that we can, first the key step, we derive the corresponding BSD of the PDE. After that, we can design the loss function. We can design loss function. For example, solution, first we do a simple reversal time. We can get the BSD, make the solution. This one is the value x0 xt. We do the capital T equals T prime equals capital T minus small t. We do the time change inverse. So this one is what we desired. In fact, it's a t. Here is t, but we do the time change. So we can, this one is what we want to solve. We will try to solve this one, theta phi. Now we design the new neural network. There are also a lot of techniques for this one because the time limit cannot get too much details. For this, this one is to generate the stochastic process, to use the explicit Euler scheme to generate the stochastic, getting the training set. But this one we get the training set to train to get U. This is a loss function. This is a loss function. G is a capital value. This is final value. By this we try to solve the parameter. The subparameter is what we desired, theta phi. Yeah, this is architectural neural network. And we can also get the forward BSD. Yeah, by this way we can solve that. We can get several use classical method and deep learning method to solve this. Then we can discuss more applications. Most of the previous work is for the physical process. Here we can consider we also try to model a telomere shortening process. Modeling telomere shortening process. It's a shortening length. We can, based on the CTRW framework, we build the model getting the distribution waiting time of the distribution jump lines. We can, the length should follow this way for the several factors to consider the jump lines. We can use to model the shortening process of the telomere. This will give an application. We calculate some statistical observables, for example, occupation time and the first passage time. And another one, we can also do the time change function Lagrange motion. We can also use the equation to use our method to do some simulation. Those are all our future works. Also more biological macromolecular motion. Use all our existing mathematical frameworks to try to extend the quantity to get more applications in the biological background. The biological macromolecular diffusion to use stochastics to characterize it. Also the biological molecular growth, and also model the use of stochastic process and the connection between process and the PDE. Because are familiar with the PDEs and the stochastics, there are some based on their connections to discuss the movement of sand by wind. We can consider several cases, and we can study from the PDEs point of view. We can also discuss the equations that couple the PDEs, and also discuss from the stochastic process, and sometimes we couple them together. And also when the fluid and the solid, and also modeling the wind and the fluid interaction to enhance the diffusion, to characterize the enhanced diffusion. And also this one is this our work. This model is we firstly build this kind of multiple internal states we can, as I just mentioned previously, you can effectively treat this case. This is the application with the bacterium. For this bacterium, this is the head of the bacterium. It cannot, this head cannot go to these three places, cannot go back to the, this is the body of the bacteria. This head can just goes to these three places. It cannot go to this one. It can also reach these places. How to use a stochastic process to describe the movement, the motion of the bacteria. We had to. That's not easy if we not use the multiple internal states. But under the framework we build, we can effectively treat the movement of bacteria. It can just go to these three places, cannot go back to, cannot reach these places. Yeah, after we build the stochastic process, we then derive the PDE, then describe the thermotaxis model for this motion. Yeah, more works is to build the Feynman-Kai adjusted, build the Feynman-Kai for all the above stochastics, establish the nonlinear Feynman-Kai for the distribution-dependent stochastic process, and also static representation for the above problems. Then we can do the stochastic analysis based on the stochastic representation to do some regularity analysis for the PDE. Now, then deep learning algorithm for the above, also the classic algorithm for the above models. Okay, thank you.
Thanks for your wonderful talk. Now it's time for questions. So at the beginning, you show this Laplace minus Laplace power beta over 2. The two kind of definition. One is using Fourier transform, the other is integration, singular kernel. So of the whole space, they are equivalent.
Yeah.
The bounded domain is their proof they are equivalent.
Yeah. The bounded domains are not equivalent.
So which one is more physical?
They're describing different physical problems.
Okay.
They're different. They're two different processes.
Okay.
One is the first killed. The process of killed is different. The killed level process with first is first killed, then do time change or killed and time change to change the order, the different order.
Okay.
And the mathematics, the different order, physically the different order. First is you do time change, then do killed. This level process. Okay. It's the generator of the process is integral form. Another one is you do first you killed, then do time change. Then is Laplace is the definition is comes from the not integral form. Yeah, the two physical process. Okay. Yeah. Physically are different. Mathematically also different.
Okay, thank you.
Hi, Professor. So could you say again, how did you use the transition matrix of the one that you wrote in the slide?
How to use the transition matrix?
Yeah, how did you use it?
Okay. Transition matrix. Oh, here, yeah. So this one, we can consider the plus is the internal state. Plus minus, for example, this internal state. This plus minus, that's the internal state. This minus plus is internal state. And minus is this internal state. So we do not allow it to go to this internal state. It implies this internal state minus must be 0. For example, you starting from this one. From this one, you can just from this state you can get From this one is this is the first one. First, this is the first, second, third, the fourth. So this one is from this direction. From for this direction, you can go to this direction. So this half 103. From this one is 103. From this one is the third of 1, 2, 3, yeah, and 2, 3, 4. From 3 to 4, this 1 to 4 is yeah, this one is 0. It means from 1 to 3rd is 0, right? 1 to 3rd. From 1 to 3rd, this direction is 1 to 3rd. So use that.
Okay, any other questions? Maybe I can ask one. Is the random walk in the beginning actually I kind of lives in KPZ universality? Is the random walk in the beginning live in the universality of KPZ?
KPC.
KPZ.
KPZ.
KPZ, yes. It is a kind of probability model that the probability density function is not the scaling limit is not Gaussian distribution, but some distribution with e exponent x1/3. Yes, is that live there, or actually we can choose the a special diffusion waiting time such that it can live in KPZ universality.
Firstly, I'm not very familiar with you said the KPZ models. Yes, we can by choosing different kinds of waiting time distribution, and we can get all kinds of PDEs, and describe the second moment and for the different maybe I'm not familiar with the model. I can we can see the PDE. Try to get what is the potential stochastic process.
Okay, it is something looks like, so normally you XX and it will add this term.
It's a nonlinear PDE.
Yeah, nonlinear, and add some noise.
Oh.
And here is okay, of course.
Okay. Nonlinear PDE, so the process is not nonlinear PDE is not the process should be, for example, when the is distribution dependent stochastic process. That kind of process have nonlinear for quantification.
Okay.
Yeah.
Okay, thanks. Okay, any other questions? If not, let's thank our speaker again.